How are we doing? You doing good? Missing a few. Boy, it doesn't show up well. Much better on my screen. This was one of the pictures shot last week. That's Monday. This was me making laser marks on the building to show up, so it looked cool. But it actually turned out pretty cool. But you can see here's the Pleiades. Here's Perseus. This one's a pretty good one. Most of the pictures, the problem with the pictures is they weren't in good focus. The focus has to be super precise. And if you look at most of them, when you zoom in a little bit, you're like, oh, the stars are really big, kind of fuzzy. And they should be just really sharp points. So this one's pretty good. It's not great. I can show you if we zoom in so you can see the stars. You see the stars start to round out. There's not all the light in the center. That's slightly out of focus. But it's not terrible. And you see that's at 400%. So that's not too bad when you get up to that amount. Here are some of the other ones. This one is that does not look good. It looks much better on my screen. Sorry. I don't know why our projector just doesn't do as good. But this is a similar area. It was just a nice shot of Perseus, and here's Cassiopeia right here. And then Perseus right here. And you see those two bumps right there? That's the double cluster in Perseus. And I think we looked at that when you looked at open clusters. You probably looked at one of those, NGC like 286 or something like that. Those are the double clusters. So let's show up pretty good. Also, when you're looking at my screen, you can see the star colors. There's actually color in the stars. You kind of lose that with the projector, unfortunately. Let's see some of the other ones that were kind of cool. I just picked out a few of the best because there are a lot of them are lousy. This was one of the ones that had the group in here, but you still had stars back here. This is the moon, okay, oversaturated. But it's kind of cool with the red glow here. And the people here kind of get washed out. I think that's the writer right there. But you can't really tell very much. But it looks cool. And when you're taking pictures like this, one of the best things to do is actually get a tree or a building or something, because it gives it that frame and it makes it look a lot nicer. Again, you have to get the focus really nice to make them look good. We've got a couple more here. Here's another one. This one was a little bit better. It's a little slightly shorter exposure. The other one you saw was a little overexposed. So here's the moon again. You can see, we can start to see the clouds coming in right here. This is Delphinus. This is Altair and Aquila, the eagle. So yeah, pretty good, pretty good. This was Jupiter. And this was, Taylor, I think this was your guys' group, had the best pictures. Better than the ones out of the 10-inch. I compared them. Mostly it was just getting a really super crisp focus. And I had to tweak it a little bit. And astronomy, you do a lot of Photoshop tweaking. I got the best one I could find. I tweaked it a little bit. I sharpened it using a filter so that the cloud band showed up a little bit better. And then I took a separate picture that had the moons in it, because you can't get the exposure to get them both at the same time. And I put them together to make a picture where you got both the moons. Well, the fourth moon is there too. This is a little faint. The moons and Jupiter on the same picture. Yeah. So, but that's pretty good. You can see the cloud band very distinctly. Looks nice. Oh, here, I showed you that one already, I guess. What other ones do we have? Oh, this was the moon, which was pretty good for the moon being about 5 degrees above the horizon. So you're looking through all kinds of stuff. And remember last week we were talking about how you get this effect as you get close to the horizon, where the red separates out. See that red edge? That's all caused by atmosphere. the moon's nice and high, you wouldn't get that edge effect at all. But that's a pretty good picture. Yeah, especially for the high air mass. This was another one I liked. Oh, you can't see as well, but you can see the Milky Way coming through here. And what's that? Anything else? Nope. What? No, wrong part of the sky.
North America?
No, it's the Andromeda Galaxy.
I couldn't see
I couldn't.
Cassiopeia anyway.
Cassiopeia is right here.
Oh, it's drowned out.
And this is Perseus, and this is the double cluster again. It's just hard to see. On my screen, it shows up a lot better, but when your projector network gets the same resolution, so. Yeah, you kind of, it's tough, it is tough to pick out right here. So, but that is the Andromeda Galaxy, you can kind of see it. I think might be most of them. Let's see, what else do I got? Oh, yeah, here and then I compared the two. This one is Pleiades with a really long exposure. It actually makes it too bright. See the Pleiades coming up right here. This is the Hyades and Taurus, that face of Taurus down here. And then we got Pleiades with a shorter exposure. But they actually made more distinct, but you still see the Hyades coming up here. This is the glow from our cameras on the building. All right, do I have any more to show you? Oh yeah, Saturn. And that was the best shot of Saturn. One of the biggest challenges with Saturn, or with any planets, is they're really bright, as you can tell, but they're actually very small. They aren't very far big across, and so it's hard to get a good crisp picture because they're so small. Now, you can do better if you do what they call projection systems, where you put an eyepiece in it and then you put your camera, which we didn't do. We just put the camera directly on there, so it was like a giant telephoto lens. But if you put another eyepiece on there, you project it onto it, kind of like what you do when you're holding your phone up there, because then you're actually projecting it through the eyepiece, which makes the object much bigger. So Saturn appears bigger. But it's way harder to hold it and get it all in focus and make everything work. If you're trying to hold your smartphone, you probably tried that, right? It's really hard to hold it and get a precise picture because everything's got to be lined up very exact. I have all the pictures that everybody took. If you want them, you can have them. If you want to do something with them, you can do whatever you want with them. So,
What if you like made a Google Drive on the, we have a,
they're really big. I mean, it's a lot of pictures. So the easiest way would be if you had a jump drive. Instead of me trying to upload it to some Google Drive and they say, oh, we don't want your 3 gigabytes.
I think I have like 80 something gigabytes on my school drive. So.
On your school drive, on your Google Drive? That is fine. We just have to figure out how to get them to you. I have them on my networked drive, but
I have one. Do we have any updates?
Yeah.
we'll figure that out. We're not going to go to the observatory tonight, not because it's not clear, it's very clear, but because the moon is just way too bright. I forgot about the moon being so bright. We won't be able to see anything. When you came in, you probably saw it. If you were paying attention, you're like, oh yeah, it's a waxing gibbous. So we're only about 3 days from full moon. And so within a few days, the full moon is just never any good at all. So we're bagging tonight, unfortunately. But we will talk about a couple things, and then I'm going to show you a few things too. So. Homework. Turn in your homework, please. And we will have class next Monday night. Don't know yet if we're going to do the turnout. Let's see. We're playing by ear. Right now, long-run forecast doesn't look great, but 7 days out doesn't tell you much.
So what day did you intend our final to be again?
The one after that, 29th.
Oh,
But out at the observatory or the one in here? We have two parts of our final.
whichever one.
Both, right? So the 29th will be out at the observatory. And that's when you'll get judged on how well you set up a telescope, how well you find things and focus and center and all that. That actually goes towards your final. So that counts 60 points. The final counts 140, so it's a 200-point final. So it's like 30% of your grade on the telescope. So don't mess that part up.
So,
And then the final will be the last class day, which I think is what, December 6th or something like that. Whatever that Monday is.
December 6th.
Is it the 7th? I don't know what day it is, whatever that Monday is. Okay.
Not the next one, but the next one.
Yeah, so we got 3 more Mondays after tonight. We got the 22nd, the 29th, then it would be the 6th. That's it. And then the class is over. It's disappointing, isn't it?
We didn't do it.
What's that?
The planetarium.
Yeah, we never went to the planetarium, did we? But usually I only go to the planetarium when it's cloudy, but we've had a really good semester.
Yes, we
We
did.
go to the real planet.
Yeah, we go to the real sky. So, yeah. Truth is, you go to planetarium, it'll be disappointing. Yeah, once compared to the real sky. All right, so more to cover though. We're gonna talk about detectors tonight. Light detectors. What's the most ancient light detector?
So when I create, when I try,
Oh, before that,
wait, what did you?
the first light detector that people used on the stars. Your eye, yes, your eye. Let's talk about your eye and how your eye works. So we're going to talk about light detectors. Your eye, how does your eye work? Good question. Yeah, you have a lens right here, right? And the lens focuses the image on your retina, the back, right? Back of your eye. If you wear glasses, it's because your lens is doing a poor job of focusing the light on the back of your retina. You have to have a correction. Okay? And it especially gets worse when you get older like me. You guys are still young. But as you get older, what happens is there's muscles here that can contract and stretch your lens. And when they stretch it out, it changes the focal length. And so that focal length change allows you to focus from really close to really far. But when you get older, your lens can't focus like that. It can't stretch and contract as much. So your vision gets worse. That's why you see old people doing this, because they can't get their lens to focus anymore. Okay, that's the problem. And the images we see are actually all upside down. Because it's a convex lens which is going to flip the image. Your brain doesn't care. Your brain focuses, takes that image and makes it right side up. In fact, your brain is very flexible. Meaning, I saw a psychology experiment where they gave these people glasses that flipped it over again. So at first they're walking around and the whole world's upside down. And they were having a hard time, they kept running into things. But after a few hours, the brain adjusted and they could see just fine. And they walked around for several days wearing these glasses and they were just fine with the whole world upside down. However, then when they took them off again, they were messed up again for several hours because the brain had to readjust again. So your brain can remap really quick. It just takes care of that. What we care about is the light comes in, gets focused here to the back, right? What is the detectors and how do they work? We have receptive cells. What kind of cells are they? Rods and cones, right. What's the difference between rods and cones?
One focus
Sure.
color and one
Yes. Which ones are colored?
color.
Cones. And how many different cones are there?
There's 3 different kinds.
There's 3 different types of cones. And what are they? No, but you're close.
Red.
What did you say? Maybe you said it right.
Red, blue, and green.
Yeah, you're right. Red, green, and blue.
It's like, I don't know what other option there is.
RGB. I thought I heard something else. Sorry. No, I thought you said yellow. Oh, no, yellow. That's it. We have 3 receptors for color. Red, green, blue. Okay. The cool thing about that is that allows us to see colors. Do we only see 3 colors?
No.
How many different colors can we see?
About 3 million.
Yeah, millions, on the order of millions. Because you can mix these colors, and if you remember from your art class or whatever, we had a color wheel. You can mix those colors and get any color of the millions of colors that exist if you just mix them in variation. And that's the way your eye works. So it really takes 3 cones to get 1 pixel of light with color information. Which means color cameras are the same way. They're never as high a resolution as black and white cameras. So rods, on the other hand, detect just light. And you get a black and white image from rods. This is how we know things like dogs are colorblind. Not because we put the colors out and say, oh, can you see this? They've done autopsy on the eye, and their eyes don't have cones. They just have rods in them. If they only have rods, you're only detecting light. Okay? Our eyes are tuned exactly to the sun, meaning our eyes have evolved to be perfect for the sun. If our planet, the Earth, had formed around a different star that was a red star or blue star, our eyes would have shifted in the spectrum. Our eyes are perfectly matched to match where the sun gives off all its light. Okay? You live on the Earth, you have these kind of eyes. Now, there are animals that see different parts of the spectrum. There's ones that can see into the infrared, like reptiles. Okay? And there's some that can see up into the ultraviolet, like insects, like bees and stuff can actually see in the ultraviolet because it helps them to pick out the right flowers. Now, our eyes, in the back of our eyes, the center of your vision has way more receptors than the outside. It's not uniform. So when you look at somebody, they're really clear right at the center. But if you don't move, the sides over here are real fuzzy, aren't they? So there's a lot less receptors over here, and it's out of focus. Now you still have the peripheral vision, and on the peripheral vision out here, way out here, not near the center, you have more rods than cones. So you have less color definition on the outside, which is good. Again, it's an evolutionary trait, because all we want to see out here is motion. When you want to see that lion coming after you out of the corner of your eye so you can react, all you want to do is catch the motion coming out of that. And so over here, you don't care about the detail. But if you want to look at something with a lot of detail, then you look and put it right in the center of your vision, because that's where you have the most receptors pushed together. With that being said, most of the receptors right in the center are cones. So one of the things we tell you to do in astronomy when you're like looking through a telescope at something very faint is not look at it. You look off to the side, and then what you're doing is you're focusing the object. So if you look on the side, then you're focusing the object, like the fuzzy patch, on the side of your eye, which is where there are more rods and it shows up brighter. It's kind of weird the first time you do it, but once you get used to it, astronomers do it without even thinking about it. It's like, oh, there's an object here. Well, I'm actually looking over here, but concentrating over there. It's just to use what they call averted vision. You're using your vision averted away from the object you're actually looking at. All right. Are our eyes linear detectors? If some object is twice as bright, does it appear twice as bright to us? No, they're not. They're logarithmic. We already talked about this because the magnitude scale is based on eyes, and it's a logarithmic system. Okay, so no, it's not a linear detector, which is good because that means we got a really large range. If it was a linear detector, we couldn't see from as faint as we can to as bright as we can. But being logarithmic, you can do that. And our eyes just adjust that naturally. All right. So basically, that's the way our detectors work. If you're curious, we can see from 380 nanometers, which is blue, shortest wavelength, to roughly 660 nanometers, which is the most extreme red we can see. That is the range of a typical human eye. Now, humans are not all the same. Some people can see better than others, of course. So some will have better vision than others. Some people that are colorblind, is anybody here colorblind? The most common color blindness is a red-green color blindness, meaning you're only born with 2 sets of cones instead of 3. And the red-green essentially blur into 1. All of a sudden, then you lose and you can't see 16 million colors. Your colors drop down to thousands.
Wow.
And red and green, you can't tell the difference of it all. They just look the same to you. Now, I don't know what color that looks like, but nobody will, because it's like, what I see, is that what you see? Nobody can know, right? If I say blue looks like this to me, does blue match you? Who knows, right? But yeah, I talk to people that are red and green colorblind, and you can hold up a red and green sock, and they're like, yeah, they just both look the same. So, all right. But the problem with your eye too is your eye can't save an image. We can look and we can say, oh, I remember that, but it's not a precise image, right? You can't take a picture and look at it later. So the first images that could be saved were done with what? Yeah, photography. By the way, I forgot to talk about, how does your eye actually work? So the light comes in, hits the receptor. What does that receptor do?
It sends it to.
Sends what? It actually releases a chemical. The chemical goes across from that to a receptor. That receptor then says, oh, I see the chemical. And it sends an electric signal to your brain, which is kind of weird.
Yeah.
But that's how you can overload your eye. If you like stare at a certain color and then you look away, you'll still see what they call an after image. You've overloaded those receptors with these colors, and so you actually see the inverse color. All right. What's photography? Photography is using a chemical reaction to create an image. Essentially, when light comes and hits this chemical, it's usually, and there's varied ones, but most of the ones that were done, especially the early ones, were done with silver nitrate.
Oh,
Because silver nitrate has the right molecular bonds so that a visible light photon, when it hits it, can actually break the bond apart. And so where light comes in and hits it, that molecule then gets split apart. And then you wash it away using chemicals, we call it developing the film. And wherever light was, the stuff goes away, but when there wasn't light, then it ends up being light. So we created what they call a negative. And then you run it through again, because a negative and negative makes it into a positive. And so you take the negatives and then you blow up the negative with a camera, and then you put it on a piece of paper, and the negatives will become positive and the positive will be negative. You guys, probably long before you, has anybody ever shot film cameras? A little bit. Back when I first started teaching astronomy, we were still using photography. I taught an observational class like this, but we would go out with camera and shoot film, and then I would teach them. We had a dark room, and I would teach them how to develop the film with all the chemicals and stuff. Nowadays, I don't know if even our photography degree teaches any of that. There's a few people that do it kind of as art things, that you can mess around and do kind of cool things, but nobody really does it for photographs' sake anymore. All right, so what I really wanted you to know that photography is a chemical reaction where the chemicals, and we would call them grains. And the grain size varies with the type of film you buy. And that's where they came up with things called the ISO speed. I don't know, are any of you guys into cameras? You change the speed, what's called the ISO. That ad came from film saying how sensitive the film is to light. The bigger the number, the more sensitive it is to light. The smaller the number, less sensitive, but the finer the grain, so you get more detail. So people that wanted to shoot these really elaborate landscapes in super high resolution. I was like Ansel Adams, I don't know if you heard me, he was a photographer, but he'd go shoot like Yosemite. But he would use this film that was super high grain, high amount of grains, but it didn't absorb much light. So he'd set his camera up and its exposure would have to be like for 2 minutes on tripods. Okay, now most people wouldn't want to do that, they want it faster. So what you do would be bigger grains, so your resolution wasn't as good, but you could shoot with faster speeds. Or back in the day, you used to use flash cameras all the time because you would just add your own light.
Thing where you hold it up.
Yeah, you hold flashes. And originally, when was photography invented?
Yeah.
Roughly
Maybe
18.
46.
Yeah, well, it kind of evolved. There's not like an exact date. Around the 1830s and 40s, they started out with something called a tintype, which is a piece of metal that was sensitive to light, and you could actually create images on it. It wasn't until they started to put it onto glass plates, which was the first one, which came around 1850, 1860. That's why the first war in the United States we had with any decent pictures was the Civil War, because Abraham Lincoln actually hired a professional photographer to travel around after all the battles and take pictures. So we have hundreds of pictures of dead guys laying around. Before that, there were no pictures. So, and he would bring all this chemicals and stuff right to the battlefield and would develop it into tents,
Oh.
the pictures. All right. Nowadays, we've evolved beyond this. We're into digital cameras, or what we call CCDs, which stands for a charge coupled device. For a long time, most of the 1900s, they realized if you have a piece of silicon, the right kind of silicon, and you connect it to an electric circuit where you have electrons coming in, electrons going out. Yeah. And they don't have to be flowing, you have to connect it to a source, right? When light comes in, a photon, a silicon molecule has just the right energy, so when that light gets absorbed, it actually kicks out an electron. Okay? Well, if you don't let the electrons flow out, then every time a photon hits, you get an extra electron. You let more electrons come in, but then they just start to pile up electrons. Everybody's taking E&M class and everything, right? You pile it up, you get a charge, right? Okay, then what you do is you let that go on for several seconds, and then you say, oh, and then we just dump out all the electrons. We just clear them out. But when we dump them out, we can count them. It's simply, you just measure the voltage, because you know exactly how many electrons make a volt. And so you just count it and say, oh, if I have this many electrons, then I know how many photons hit or how much light hit it. That was a silicon detector. And they've had those for a long time. That was very painful to use in a telescope because you'd have to go look at whatever you want, like your star, and you'd have to have this little circle and it would only let the light in from that star, because if there was any other star, it would add all of the light that was in there. So you had to just do that, and then you would have to move to another star because you have to compare it to another star, and you have to be moving back and forth and trying to make sure you centered it exactly. Back when I first went to college in astronomy, my grad class, they were still doing that. I was using a CCD chip, but there was a guy that was doing a study of Pluto, and he was still using the silicon detector method, and I helped him out one night. I'm like, wow, this is a painful way to do it. But they realized, okay, let's just take that silicon chip and make a big chip but break it up into millions of these. So every one of those little squares, which we call a pixel, is essentially an individual silicon detector. It just counts up how many electrons hit it. Well, if you count up in a whole area, you make a picture. Okay. And like I was saying before, the finest detail comes down to how big your pixels are. The finer the pixels, the higher the resolution. When digital cameras first came out in the 80s, they were very low resolution. The first digital cameras on phone were 256 by 256. Totally out of focus, you could hardly see anything. They were terrible. Now you can buy one that's like 100 megabyte, 100 megapixels. And you're like, okay, yeah, things have come a long way, haven't they? Yes, and originally, these were actually developed in the 70s. They were going to use them for electronic storage as a means like a hard disk. And they realized they were way more valuable as a light detection method. The Hubble Space Telescope, when it first went up, the biggest chips in the world were made for it. They were 800 by 800. So they were still very small chips, and they had to put 3 chips together to try to make it bigger. So the first picture you see from the Hubble actually had this weird configuration because they had multiple chips they were trying to put together to make it bigger than it was. Good thing about the Hubble Space Telescope is they left it in low Earth orbit so they could go back up and fix it. So after about 5 years, they went up and put a new camera in, which was way better because all of a sudden technology had increased significantly. So they put in much better cameras, and they've done that a couple of times. All right. So the idea then is you get all these pixels and all these electrons pile up in these different things. And how you read off the image is you can't just flush it all out at once or you lose all that information. So you actually have to move it over, which you can do. You just change the voltage. It shifts it over, and then it comes out and you read it one row at a time. When they first made these and I first started using it, you would take a picture. You might take like a 10-second picture, then you'd wait like 50 seconds for it to download because it's really slow to read across and down. Well, the electronics are kind of so good now they can almost instantaneously read this whole chip, which is great. And they keep getting better all the time, as you know. So you just read the whole chip off simultaneously. Again, if you want color, each of these is just reading the amount of light. So if you want color, what you have to do is you have to make one sensitive to red, one to green, and one to blue, and then you combine those 3 together to get 1 pixel. So you're actually reducing your resolution by 1/3. Because the pixels have to only be sensitive to that 1 color band. And you count the number of colors in there. That's why in astronomy on big telescopes, there are no color cameras at all. But you say, but these Hubble has these beautiful color pictures. Well, what you do is you just take 3 pictures. You take a picture through the red, a picture through a green filter, a picture through a blue, and then you combine them together on your computer and make it into a color picture, which is how we do color pictures too. Is we just have them, the 3 different ones, and we combine them together over time. All right. The other thing, advantage of CCDs is they're linear detectors. Where photographs were actually logarithmic detectors like your eye, which is why people like photographs, because they actually match what you saw. But a digital detector really doesn't. So you're saying, oh, but when I take a picture, it matches what I saw. Yeah, that's because they smoothed it over to make it look like what you see. There's a whole bunch of software going into your digital camera. If you have like a SLR camera or your camera on your phone to make the picture match what you see. If not just directly there, because it would look slightly different and it wouldn't match your eye. Everybody wants it to match what you see. So they do a lot of software on it. This is really good for astronomy because if you're comparing 2 stars, one has twice as many electrons as the other one is twice as bright. you don't have to figure out what this logarithmic function is and how it varies. So it's makes these really good for astronomical detectors. And they're very highly quantum efficient. Most of these are on the 90% quantum efficiency. What's quantum efficiency? That means that 90% of the electrons, the photons coming in, the light, gets detected by the detector. Photographs are on the order of about 10% or less. Same thing with your eye. Your eye is actually not super quantum efficient. Depends on your eye. It also depends on what animal you are. Some animals are actually more efficient than others. They got better rods than others. Animals that live in the dark have very good rods and are very sensitive to the dark light. In the dark, much more than we are. Nocturnal animals. All right, so this also makes it very good because in the old days, we used to take pictures. To get a picture of a nice galaxy, you might have to take a picture for like 2 to 3 hours on the same object. And now you can do that picture in a few minutes and it looks great. So it's really nice. And because they're linear detectors, you can take a whole bunch of pictures, you just add them together. And the more you add them together, the better the signal gets. Okay? One of the things that we have to worry about is when you take pictures, how big your resolution is. Well, it depends on what your telescope is. So for like our 27-inch telescope, which is the big one that you looked through a few weeks ago, it has a scale of 0.608 arc seconds per pixel. The smaller that number, the higher the resolution, or the better detail you can see. But as we talked about before, you're also limited by the atmosphere. And the atmosphere around here only gets down to about 2 arc seconds ceiling. So you can't really, you never get smaller than a pixel. Yeah.
The smaller number, the what?
So this is arc seconds
Yes.
per pixel. So, for example, if I was looking at a star, remember we talked about last week, stars spread out? And we talk about the scene or the full width half max. Let's say this is about 3 arc seconds across. That's typical on a typical night for around here. How many pixels would this be across? Well, if this is 3 arc seconds and this many arc seconds per pixel, you just divide them. So what's 3 divided by 0.608? 5 point what?
4.934.
Okay. 4.9 is good enough pixels. Which means on your chip, the star is actually going to cover about 4 pixels. Okay. For a star, you just want it to be as tiny as you can make it anyway, right? Because that means it's in focus. But this becomes a big deal if you're looking at a galaxy or a cluster, right? One of the things that some of the groups last night tried to take a picture of through the 8-inch, I think you guys tried to take a picture of Pleiades. Did you see the whole Pleiades? No. The problem is the Pleiades are too big. They're like a degree across. So on our 27-inch, we have this, but our camera is 2048 by 2048 pixels. So if you just multiply that out, you get that the scale of the camera is we can see about 20.8 arc minutes by 20.8 arc minutes, which is about a third of a degree, right? So something like the Pleiades, which is over a degree across, you can't see the whole thing, you just see parts of it. Okay? Even the moon, what size is the moon? Remember? What is it? Half a degree, which is how many arc minutes? 30, yeah. See, it's still too big. The moon, you can't even see the whole moon in there either. So make sure you write this down because you need this for your homework. We also, on the back of our 27-inch, have a refractor. Which is a 5-inch refractor. Made by Takahashi, so that's what we call it. It's the Takahashi. Just because it's fun to say. But because it's a lot smaller, it has a shorter focal length, it has a bigger field of view. So it's on a scale, it's 3.428 arc seconds per pixel. Which means with the camera that's on it, you can see 1.95 degrees by 1.247 degrees. So you can see a lot more in the sky. Easily you can get the moon in there. In fact, you get the moon several times over. Yeah, those are both degrees. Don't get confused because I switch between things, right? Arc seconds, arc minutes, degrees. Yeah, 1.95, yeah, 5 arc. It's a 5-inch refractor. All right. Now, when you use CCD cameras, or there's things we have to do to correct and make the images work the way they're supposed to. But we're going to deal with that next week. So next week, I'm going to show you how to take images, how the images that I've taken before, and how to take those images and what we call reduce them, get rid of all the electronic noise and the noise of the instrument, and then put them together and make a color picture out of them. So we're going to do that next Monday. Okay. But what I want to show you right now, if I can make this work, because it was freaking out earlier, is even though it's clear outside, I want to show you how we run our 27-inch telescope and how we take pictures with it and how we do research.